Right, wonderful people, you remember this is where we left off, and I explained that the angles at the center are 2 times the angles at the circumference, and I even said that they don't have to be the vertex here doesn't necessarily have to be pointing to the angle at the circumference. You can have this point in here or in there or even in here, or you can have it there or even here, as long as they are in the same segment. This is very important. So what I'm trying to say is the following: we can have a circle. Suppose that's a circle, and it's fine to say that we can have an angle at the center. Let's say this is the center. Let's have our center there, and we can have let me just do this so that we have this segment and the other segment. And what I can do, I can take this angle and try maybe and put it in there. So what I can do is the following: I can have it like this, you see. So suppose this is the center and the angle there, it's 80. So we are therefore saying angles at the center are 2 times angles at the circumference. So let's say maybe this is AC B, ABC. So if O is the center and this is segment 1, for example, and this is segment 2, therefore we are also saying angles at the edge. This is very, very important because this is an edge. The angles at the edge are half the angles at the center. So this is very important. If this is 80, this would be 40, because you have the center and you have an angle at the circumference, and we know that angles at the center are 2 times angles at the circumference. So what I'm trying to show is they don't necessarily need to be facing each other in this way. No, even if the vertex is not pointing to the other angle, as you can see in here, the vertex is not directly pointing towards that. So you would ask yourself if the theorem still applies. Yes, it still applies. Why? Because this is an angle at the center and this is the angle at the circumference. And one thing that is very important for you to note here is the following: A and D comes together to produce a center angle. A and D comes together to produce an angle at the circumference. So the theorem still holds. Angles at the center are 2 times angles at the circumference. Let's see if the same is happening here. A and B comes to produce an angle at the center. We have been told that O is the center. Look again, A and B comes together to produce an angle at the circumference. Therefore it still holds. Angles at the center are 2 times angles at the circumference. I hope you understand that. But we're going to deal with exam related questions. I think it will be much clearer for you to know and understand, and the level at which these questions can be asked. Right, we are done with this. Let's now go and look at the tangent radius theorem. The tangent radius theorem. So you have a circle and you have a tangent. Remember, it's a straight line that only touches the circumference at one point. This is what we call a tangent. You have the center, and here is a radius, because the radius is the distance from center to any point on the circumference. But in this case, the radius is perpendicular to a tangent, meaning they produce an angle of 90 degrees. So let's say you're having a line that comes from the center that is perpendicular to the radius. So what does that mean? It simply means that OBC, in this triangle of OBC, angle B will always and always be equals to 90 degrees. And what is your reason there? You'll say tan radius theorem. That would be your reasoning there. Whenever you have a radius that is perpendicular to a tangent, they will always produce an angle of 90 degrees. Okay, that is fine. Be that as it may, now let us look at the tangent chord theorem. Tan chord theorem. Now, meaning here you have a tangent and a chord. A chord being a line that doesn't pass from the center of the circle. So you will have a chord. For example, let's draw the first one. This is a chord. It's just a straight line that touches two sides on your circumference. And we can have another chord like this. Very important. And let's have another one in such a way that we draw up something that looks like a triangle. And therefore we are saying, if this is A, this is B, and this is C, and we have a tangent here. Remember, we are speaking about the tangent and a chord theorem. So you're having your tangent and you have a chord. So whenever you have a tangent and a chord, what is it that you should know? You should know that this angle in here, the angle here is equals to the opposite interior angle. The exterior angle is equals to the opposite interior angle. This is very important. Whenever, because we have drawn this in a triangular format, we are saying whenever you are having a chord and a tangent, the exterior angle is equals to the opposite interior angle. So meaning the exterior angle is equals to the opposite interior angle. This is very, very important. Whenever you have a tangent and a chord, a tangent and a chord, the outside angle is equals to the opposite interior, as you can see in here. This is what we call the tangent chord theorem. Very, very important. So for example, if we're having this tangent BF, we can therefore say in here, we can say, if we take this chord, we can say CBF, meaning we are saying angle B. In this chord you have a chord and a tangent, therefore we are saying CBF angle B is equals to angle A. Please be very careful. We have shown that there it is. You're having a chord and a tangent. Therefore we are saying, because this is a chord and this is a tangent, we are saying CBF in CBF angle B is equals to angle A. And what is the reason for that? The reason is tan chord theorem. So meaning we can come back and say, for example, let's say A, B, C, let's say this is D, such that we can say that A, B, D, in ABD angle B is equals to angle C. Can you see that? in ABD, angle B is equals to angle C. And the reason is tan chord theorem. This is a very, very important theorem for you to see. In this is equals to this. In this is equals to that. Something worthy of noting. And then now let us look at the tangent from a common point. Tangents from common point. So if you have a circular object and you have two tangents that are drawn from a common point, this being a common point, this, what is it that we know? If this is A, B, and C, all you need to know is that AB is equals to BC. Sometimes this would be shown with lines like this, just to highlight for you that AB is equals to BC. So reason is tangents from a common point. So meaning it reminds you more of an isosceles triangle, because if two sides are equal, you would argue, maybe if we draw up a line in here, you would argue that this is equals to that, but we're not doing that here. I was just trying to demonstrate for you. We're not saying in here isosceles triangle. Why? Because this is circle geometry and you have tangents. Remember, this is a tangent. This is not a triangle, it's a tangent. So you can't say angle A equals angle C, therefore reasoning here is isosceles triangle. No, angle A equals angle C, tangent from a common point, should that be the case, of course. And then when we are done with that, I can show you many different ways of a tangent chord theorem. Now let's go back in here so that I may demonstrate something for you. You can have a circle, please do not be deceived, and you can have a tangent like this, and you can have something like this. I'm sorry for my drawing. And if this is A, B, sorry, let's say B is in here, you know that the angle here must be equals to the opposite interior angle there, and you know that the angle here must be equals to the opposite interior angle there. So they can rotate this in different ways, but you always need to know your stuff. You highly need to know your stuff, right? That is all what I wanted us to look at. And then there are four main ways to prove a cyclic quadrilateral. So let's look at the four main ways to prove what we call a cyclic quad. Right, you know that if you have a cyclic quad, for example in this way, you know that the exterior angle is equals to the opposite interior angle. And you also know, for example, when you have something like this, when they form a bow tie, you know that the angle here, for example, is equals to the angle there. Please note there not need be a circle there. And then you also know that when you have a four-sided figure, the opposite angles are supplementary in a way that they add up to 180, and then we spoke of some other common ways of looking into this. So in the second tutorial we will try and apply this and see how the questions are being asked.